We have studied uniform quantizer for a uniform PDF, and we have also studied how to do uniform quantization for the case when the PDF is non-uniform. The uniform quantizer for a non-uniform PDF still restricts the step size to be uniform and equal to a constant except for the last n intervals of your input range. So, next question is it possible for us to make it little more generic and have a variable step size? So, if the motivation for this is as follows. If the input distribution has more mass near the origin, that means the probability of occurrence of the input is high about the origin, then the input is more likely to fall in the inner levels of the quantizer. Now, we have seen that in the lossless representation of the source, that is lossless source coding, in order to minimize the average number of binary digits which we require to represent a symbol from the information source, we assigned shorter code words to those symbols that occur with higher probability and longer code words to those symbols that occur with lower probability. So, in analogous fashion, in order to decrease the average distortion due to quantization, we can attempt to approximate the input better in regions with high probability, perhaps at the cost of worse approximation in regions of lower probability. Now, we can do this by making the quantization intervals smaller in those regions that have more probability mass than those intervals which have low probability mass. So, what we will get by this is that we will get smaller quantization intervals near the origin. So, if we have quantization level say L to be constant, then what will happen is that we will get larger quantization interval away from the origin. So, when we have a quantizer with non-uniform intervals, then it is known as non-uniform quantizer. Now, we will study this, and so the problem is as shown in this slide. Suppose example, I have a PDF of this form, then what I want that since the probability mass is high here near the origin, I start allotting my quantization intervals such that near the origin the step size is small compared to as we move away from the origin, correct? Fine. And we, in this regard, we will study this non-uniform quantizer, and it is also popularly known as Lloyd-Max Quantizer. The first algorithm to obtain the values of the quantization decision boundaries and the reconstruction levels for this non-uniform quantizer was provided by Lloyd and Max, and that is why it is known as Lloyd-Max Quantizer also. So, recall that for uniform quantizer, our minimization problem had only one variable which was in the form of the step size which was constant. Okay. Now our problem is a little more complex. We need to optimize with respect to decision boundaries and the reconstruction levels. So our decision boundaries, dB denotes the decision boundaries. These are B1, B2 up to BL minus 1, correct. Remember, this is for unbounded PDF. So B0 is going to be minus infinity for generic and BL is going to be plus infinity, and your reconstruction level, which is RL, is equal to Y1, Y2 up to YL. So now we have to minimize our quantization noise, which is a function of this decision boundaries, and also of the reconstruction levels. And this we know that can be written as follows. So our problem is like this: input output mapping for the non-uniform, we will assume mid-rise quantizer. I have my decision boundaries B1, B2, B3, B4, B5, B6. It is going to be symmetric about 0, correct, mid-rise quantizer. I repeat, B0 is assumed to be minus infinity, BL is assumed to be plus infinity. Your reconstruction levels have been shown here: Y1, Y2, Y3, Y4, Y5, Y6. So anything lying between B5 and B6 would be given reconstruction value of Y6. Similarly, between B6 and B7 would be given the reconstruction value of Y7. So our problem is basically to determine this decision boundary points and to determine this reconstruction levels. Okay. So we solve this problem. Let us first take the derivative of this with respect to boundaries Bj and also with respect to Yj. So first we will take derivative of this quantity with respect to Yj. Now when I do this, basically in this, remember that only one term in this summation will remain after the derivative, and that is easy to see this. What I will get is from here and this will be a minus sign here, okay, fine, and this is equal to 0, I have to equate. So if I do this, basically from here is easy to see that I will get my value of Yj to be equal to So this is nothing but the centroid of the PDF in the interval between Bj minus 1 and Bj. So Yj is a centroid of that interval, fine. Next we have to take the derivative of this with respect to the boundary points Bj, and to do that basically it is important for us to understand that this quantization noise which is equal to this expression consists of following terms. There are some terms out here, plus you will have Bj minus 1 x minus yj squared plus and there will be some other terms. So, when you take the derivative of this with respect to Bj, these two terms are going to be involved, rest of the terms will go to 0. And now, to take the differentiation of these two terms, we will again use the Leibniz rule. Given this function, take the derivative with respect to x parameter. This is the first term and these are the other two terms which we get. Correct? Using this relationship, very simple in this case, unlike what we did for the uniform quantizer and the non-uniform PDF, simpler than that here. So, if we do this, that apply this rule to this case here, we will get the following thing. Rest of the terms will go to, remember when I take the derivative here with respect to Bj, rest of the other terms will go to 0, only these two terms will be involved, and the output from there when I take the derivative equal to 0 implies I will get so this implies that now this will imply that Bj minus Yj is equal to Yj plus 1 minus Bj, because your Bj is greater than Yj and Bj is less than Yj plus 1. Look at this convention which we have followed for naming the boundaries and the reconstruction level. So, from this it is easy to see that this condition is satisfied, and from this we get, this implies that Bj is equal to Yj plus 1 plus Yj by 2. Here we see basically that your boundary points Bj is the midpoints between the two reconstruction level. Recall for the uniform quantizer, it was the other way around. Reconstruction levels were midpoints of the decision levels or decision boundaries. Okay? So, now we have to solve for this Yj's and Bj's using this equation. So, we have two equations for yj is the reconstruction level and this is the, now we have to do this in a iterative manner because both are interlinked, and one of the first algorithm to do this was basically what was known as Lloyd Max algorithm. We will quickly have a look at that algorithm. So, we have to design L level symmetric mid-rise quantizer. Your given PDF is symmetric. So, now a problem for finding out the boundary levels and the reconstruction levels reduces to what I have shown in this figure. We will compute it only for the positive side, and I have shown here basically this boundary. So, I have shown here basically the decision boundaries and the reconstruction levels. What we would be interested is in obtaining B0, B1, B2, B3, Y1, Y2, Y3, Y4. Once we get this, then immediately we can get the other decision boundary points on the negative side and we can get the reconstruction levels on the negative side. It is just symmetric. So, using this notation, we can, our problem is to obtain the reconstruction levels and the decision boundaries as follows. That is your RLs y1, y2 up to yl by 2 and decision boundaries b1, b2 up to bl by 2 minus 1, correct. And the reconstruction levels for the negative side here and the decision boundaries for the negative part will be obtained via symmetry. Okay. Just going back to this equations, this equation, we can write the value for y1, correct. So, my first y1 is equal to b1 b0 x divided by fine. So, the way we have assumed, again I show you the slide, B0 is 0, correct. So, B0 is 0. Then what we do is guess y1 and solve for b1 numerically from this equation, correct. So, I will get my b1. Now, we know that b1 is equal to y2 plus y1 by 2. So, this implies that my y2 is equal to 2b1 minus y1. So, I will get my y2. Once I do that, I know my y2 is related to b2 as follows. So, what I do is now solve for B2 numerically. Using this equation. And we know that B2 is basically the midpoint of Y3 and Y2. So, I will get my y3 from here to be equal to 2b2 minus y2. So, I continue like this process until we obtain a value for the following reconstruction levels and the decision boundaries. Now, the accuracy for all the values obtained at this point depends on the quality of the initial estimate of y1. Now, we can check this by noting that yL by 2 is the centroid of the probability mass of the interval BL by 2 minus 1 BL by 2. Now, we know this BL by 2 from our knowledge of the data, correct. So, if it is unbounded PDF, it could be infinity, correct. So, it is simply the largest value that input can take, and we are aware of this. So, I know my BL by 2 minus 1, I know my BL by 2 from the knowledge of the input data. So, I could have calculated my YL by 2 using this relationship. But remember, once I get this quantity out here, I already got my YL by 2. So, YL by 2 I am getting from two places. So, let me call the output which we get using this and my knowledge of BL by 2 as y hat L by 2. This I can compute as follows. Is a centroid. Now, you compare this point with what you have got from your calculation, because once I get this point and I know my YL by 2 minus 1, I can get my YL by 2, correct. So, now compare this with the previously computed value of YL by 2. If the difference is less than some tolerance threshold, we can stop, otherwise you will have to change the estimate, and the estimate of y1, that is your initial estimate, will be in the direction indicated by the sign of the difference between what you have got here and what you have obtained using this boundary point and the earlier reconstruction level, and then you repeat the procedure. Right? So, this is how you do it, and so in the literature you will find that again the table has been provided for the Gaussian and Laplacian PDF, again assuming that we have unit variance for different levels 4, 6 and 8. So, for 4 levels you will have two boundary points, one is obviously 0 and the other boundary point is there. For the same you will get the reconstruction levels. So, similarly for the Laplacian one, 6, 8 levels also have been given. We notice one thing here also, look for example 8 level, the Laplacian signal to quantization noise ratio comes out to be lower than this, right, because Laplacian has a heavier tail, that is the reason. And one more thing is that this quantizers give you better performance compared to 8 level PDMF optimized uniform quantizer. Right? So, you get some improvement both for the Gaussian case and for the Laplacian case. Okay. Now, again the question is how good are these quantizers? These are quite good quantizers provided we have a good knowledge of the PDF of the input with all its parameters. So, the same comments which we made for the uniform quantizer with non-uniform PDF holds good. There could be mismatch. The mismatches could be that we know the PDF of the input but not sure about the variance, or we choose a wrong PDF itself. In both the cases basically the performance deteriorate. Now, in a practical scenario sometimes it becomes difficult to implement this kind of non-uniform quantizers. So, the idea is basically, is it still possible to get good performance and exploit the ideas from what we have learned so far and design a uniform quantizer. For example, if you take a speech signal usually has heavy mass around the origin, but we may not know the exact PDF or its variance. So, is it possible for such signals to design by using some kind of a preprocessor before we send it to a uniform quantizer? So, my job is basically take this signal, input signal, use some kind of a preprocessing and then apply a uniform quantizer on it and see that this preprocessing is a reversible transformation. So, at the receiver basically I can get the proper values by using the inverse reversible transformation. So, in conclusion, Lloyd-Max Quantizer, which is a non-uniform quantizer, is also an optimum quantizer in the sense that it minimizes the mean squared quantization error for the given number of quantization levels and the input PDF. Now, the performance of this quantizer could deteriorate severely due to mismatch. The mismatch could be due to the wrong estimate or choice of variance for the particular PDF or the wrong choice of PDF itself. In practice, implementation of non-uniform quantization is always a difficult task. So, in practice, this non-uniform quantization is achieved by the process known as compounding. In compounding, the signal before quantization passes through a compressor characteristic which really stretches out the lower amplitude of the signal and compresses the higher amplitude of the signal, and then it goes through a uniform quantization process, and this is followed by an expander characteristic which is the inverse of the compressor characteristic. So, this process of compounding we will study next time. Thank you.